what are the features, but I'm just going to tell you that these are old-fashioned solutions, which will not be used in integrated designs. So we're going to introduce a few of the biasing scheme and going to discuss what are the pros and cons of these circuits. So for bipolar circuits, our biasing circuit for, let me just emphasize, this is for discrete BJT circuits, meaning that you go get the transistor as a discrete component rather than having that in an integrated circuit. So for example, so we're going to introduce one is called, referred to as the simple bias scheme. This is the most simple one. Simple bias scheme. So if you think about it, bipolar junction transistor, one of the key things is that you could actually set your biasing. Typically, what we wanted to do is to set, rather than setting VB, typically what we want to set is IC.
I think that will be something that we cover on today. So basically, some basic concept of will be 5 single choice questions and 2 calculations. We don't have multiple choice questions because you said that's not good for your grade. Yeah, so we skip that. I made some changes. Okay? So if you have any feedback regarding quizzes or suggestions regarding midterm or scheduling, any suggestions are welcome. Okay? So, but still, there's a lot to cover for this class, so we still need to move on to discussion on amplifier design. So today we're going to actually go into the, I think it's the core of this class is how do you actually analyze a circuit, or how do you start actually the designing process of a circuit. So this is like the entry level of the first step. We call the 101 of design, designing a circuit. So what we're going to do is that, just to give you a sense of what we're going to talk about today. First of all, the main analysis will be mostly focused on biasing of a circuit. Like I said, the performance of a circuit, it depends a lot on its where it stands, the operating point. So how do you actually place a circuit, its biasing point, biasing circuit, just to make sure that your players are actually at the particular location that is designed. It's called the biasing design. So we're going to talk about how does one do the biasing, make sure that your circuit is actually standing at the point where you want it to start operating, to process the signal. And then once we have this, then we can then talk about small signal analysis, mainly the small signal parameters, and then you establish a small signal model and then do the analysis. So there will be 2 parts. One is for DC analysis, first to find out where you stand. The other is that to do small signal analysis, mainly, so this is just for us to set or find, we call the Q point. Okay? And for small signal analysis, then what you actually want is to find out the behavior of your circuit, which is mainly through the understanding, the finding of GMs, R pi, RO, your small signal model, and we want to get your input resistance, voltage gain, if we're dealing with voltages. These are the key parameters you want to find out as your small signal behavior as an amplifier, for example, voltage amplifier. You need these 3 key parameters describing how this amplifier works. Okay? So first of all, one of the key things of biasing is, one of the key things is to make sure that your circuit or your device is operating in active mode. So how do you actually do the placing or finding the optimal operating point? Well, mainly it depends on the behavior of overall circuits. So first of all, what we wanted to do is to, as I said, there's two procedures. Let me just go through the procedure. The first procedure is where the Q point should be. First of all, you determine where it should be. So how do you do that? You do a survey. What's the survey? It's a large signal analysis. You do a survey of the arena first and then decide where's the point where if I'm standing right here, I get the best acoustic response, for example. So these are, you do a large signal survey, surveying whole range of the operating frequency. And then, of course, this would then depend, depending on where it is, will depend on the survey, and of course, the other thing will be depending on your spec. So what do you actually want to achieve? Mostly these specifications are power related. I'm going to talk about that. So I'm going to give you, for example, most of the example will give you that what is the maximum power I can offer with this circuit. So that will determine where you will be able to stand, or the best location, or limitations on the biasing condition. So power will typically be one of the key things to determine your biasing condition. Power meaning your ECC as well as ICC. So whatever can be supplied from the system in terms of voltage and current, that will actually limit where the Q point will be. So these are the basic guidelines, and then of course there's other specifications, mostly related to large signal behavior, such as swing. I'm going to talk about that a little bit, and linearity. Where I stand, for example, if I'm using this platform as an example, if I want to find the best place, I'm going to give you a speech. First, I do a survey and find, okay, this is my best point of having acoustic response, for example, the small signal behavior. But still, if I'm doing a little dance on the side, for example, if I'm thinking this is the best place for my best acoustic response, for example, that's an analogy to providing the maximum gain. So if this is the best place, but if I'm not doing any dancing, I'm just standing right here, this is the best place I'll do, it will be fine. But if I'm doing a little dance, I might fall off the stage. So that's why I want to talk about something called a swing. Swing meaning that actually the signal is slightly larger than we expect. So my output signal is slightly larger, then I want to make sure that I'm not falling out of the operating range. So I'm going to talk about how you determine where you stand will be depending on just not one index. There's multiple indexes you need to decide how to do it. And the last thing we're going to address a little bit on is stability. So how do you actually do this? This will relate to the type of biasing circuit. There's various ways of placing my actors or singers to this particular location. If you ever go to a concert, you have all the singers standing on the stage, all kind of fancy stuff. Those are supported by a team, which allow the singer to always standing at this particular point. So this circuit itself, how do you provide stabilized standing of the singer? It's very important because you don't want, if you have like a 10-day concert, you don't want the third day that the singer fall down to the ground. So you want stability. Okay? So we're going to talk about that a little bit. How do you actually build a reliable support for the circuit to be always at this particular location? That will be something we call biasing. How do you evaluate multiple types of biasing circuits? So as I said, one of the key things we wanted to We're going to go through a few of the biasing design, and then we're going to talk about how you actually select your Q plots. So let's say I just wanted to bias my, like I said, for a biasing circuit, then we start with giving a specific requirement. Mostly to set IC or VC or target value or target level. So let's think about firstly a common emitter structure. So this is my common emitter structure. So let's think about this is called a simple bias scheme. So we're going to introduce a few of the biasing. So if I'm doing a biasing of a transistor, the first thing you need to think about for a BJT, you need to provide collector current and base current as well. So one of the way of doing biasing is like this. You have this current pathway that allows you to establish a current level IC. Okay? But if you simply do this, there's a risk of not knowing what the collector voltage will be. Because the collector voltage, if you actually think about it, what is the cross is VC is a very, if you don't consider early effect, for example, if I'm only consider first order approximation, this is a current source, meaning that the voltage level is undetermined. If you ever do a spice simulation, you'll find that there's no determination of the current voltage level of the current source. The voltage level of current source is determined by the external circuit. Therefore, because you don't know this, therefore the current is unestablished. So then how do you actually set the position? This is like floating in the air. You don't actually know where it's going to be. Or a lot of uncertainty. That's the way to place it. So how do you actually make sure when you set operating point, one of the key things is certainty. You want to make sure that I'm standing right at this particular point, and there's a little minimize the uncertainty of it, or you want to make sure your control is very strong. So the way to do this is that I'm setting up base current instead. So what is being done is I'm applying I need to supply a base current and I use a resistor to establish this current. So if this is my setting, then think about what is being determined. So if you look at this pathway, this is IC. This is IC I want to determine. So in this circuit, if I'm using a constant voltage model, in this example, so all of this, we assume that Q1 has a VBEon, constant voltage model of points, for example. There's a fixed VBEon for this particular circuit analysis. So how do you actually find out your biasing current? We'll want to find out this mostly IC because this related to find the collector current, because this will then determine all my small signal parameters, right? So how do you determine IC? As I said, because I don't know what VCE is, I have to start with here. I already know that this is a constant voltage model, this is VBEon. Therefore, my base current is defined. Defined meaning that I could have more certainty in determining the current level. So IB will simply be the voltage divided by VBEon, which is the voltage across here, and divided by resistance. And then what is my collector current? My collector current will then be beta. Okay? So this will be simply, if you want to write it down, it will be beta RB ACC minus. Okay? But of course, in this design, you want to make sure that the picking of RB and RC, you want to make sure that this resistance is not very high, because you want to make sure. The other thing to do to ensure this is correct is to check if so at the end of this analysis, if I give you this question and give you all the parameters, when you find this out, you want to make sure to check whether this is larger than VCC. That's to say, you want to make sure VCC minus ICRC is larger than 0.4 to ensure that your transistor is in active. As I said, you want to make sure that the devices, the transistor is operating in active mode. Otherwise, these models doesn't fit. Okay? So this type of question will be in the exam. How do you actually find out these currents based on the particular model? Okay? So this is the first type of design, but there's of course some little drawback of using resistor or base current biasing. One of the key issues in this type of simple bias circuit is, let me just write a few of the problems. One of the problems is that you have to know that resistors, resistance are this is to say that if you ever did any integrated circuit design, you would know that there's a tolerance of resistance level. Most of the time, maybe 10% tolerance, meaning that if I'm designing this to be 100 ohm, it will be 80 or 150. It will not guarantee to give you a precise number. The precision level of the resistance value is very hard to get. Okay, so you have to live with a possible variation in these elements. So once we have this, that means that your base current will actually vary by 10%, for example, or even 20%. And then the other thing is that one of the parameters, theta, is hard to control. And actually varies from device to device. It shouldn't vary between devices, meaning that even though I tell you that data equals 100, most of the cases in circuit design you have to view as I can ensure that data can be as high as 100. All of them are larger than 100, but I cannot guarantee all of them are 100 precisely. It will be a range, for example, 100 to 500, for example. So there's a lot of variation of the parameters that you cannot control. So you don't actually want your collector current to be determined by these largely uncontrollable parameters. Okay? So that means that especially in this type of circuit, if your beta is too large or your resistance is too small, you will then blow up this current and then suppress this transistor down to saturation. That's the worst scenario because even though you're not at the best location, you don't want to fall off the stage. So if you can stand on the stage, even though the component is poor, it's fine. But if you can have certain design which will will easily make you fall out of the stage. That's not a what we call a robust design. The one that your design has a lot of tolerance to variation. For example, even though it's raining outside, we can still see very clear signal. That's what. Okay. So what is it? So the other type of design we're going to talk about a little bit is called. This is very commonly used in our example, but not actually in the circuit. We're going to talk about it a little bit. So if you don't want to control the base current, the other thing you can do is through voltage divider biasing. So this is biasing through VBE. So if you're biasing through VBE, then the parameter we use is IS. So IS will be provided using exponential model through the control of exponential. So you're setting up your current to the exponential model. This is not a very stable solution, but it's an alternative. So if you don't want to have your collector current be determined by beta, then the other type of design will be independent of beta. So this is also a common collector, common emitter structure circuit as an example. And what we actually use is through the supply voltage, I'm doing a very simple resistor divider type of circuit, and then set this particular point. So through this divider, I'm setting up VBE as a voltage biasing system. Okay? So we can make some assumption first. So if we assume IB is smaller than I1. Let's say I1 is the current coming down. So this is IB. So if you assume that the direct current path, which is allow us to set the voltage level of the base terminal, is much larger than this, then we can actually make our life easier, which is the point Vx, the x point. Let me highlight. This is the x point. So I'm setting up this voltage. So Vx is approximately, I could ignore this base component, base current component, R1 plus R2 will be. Therefore, my collector current will simply be IS exponential model. Remember, that will be Vx. Okay? So this is very simple. You use the exponential model to set up your current level simply by using this exponential model, setting up this voltage at the base, and then in turn set up my collector current level. So if for example, if your resistor level is slightly high, for example, R1, R2 is very high, then we cannot ignore this. This is not true. To consider, if you want to consider IB, you can actually do that. To consider RB effect, then what we actually do is through the first class that we introduced, semi-equivalent model. So this is R2, R1. Okay, so you can actually make an equivalent circuit out of this. This will be V7. And then R7. So you can actually find out what your V7 is. What's V7? It will simply be R1 plus R2. R2 will be VCC. And R terminal will simply be the parallel of the two. go back to our guidelines of finding out feminine equivalent circuits. And then R7 will simply be R1 and hello R2. Okay? So then your equivalent circuit will be, and how does one calculate this? So then your circuit will look something like this. V7. Okay? So then you can actually find out your voltage level here. There will be a slight difference. So this will still be my Vx. So Vx will simply be V7 minus IB R7. Okay? And the current level, IC, will then be IS exponential EX. The current will still follow the same equation. The only difference is that there's a slight correction on your V. Rather than simply the voltage divider results, you have to take away the drop on the resistor. It's a slight resistance effect. Okay? We can actually go through an example, so to just give you a sense as to how much do you want to pay the price of being precise? How much do you want to pay to get precision? So how much precision there is? Or if you simply use this model, how much precision did you lose? So I'm going to go through a simple example so that you get a sense as to which model you can pick. So let's say we assume that I have a relatively large, let me write down. For VCC, let me get the parameters. So let's say if my VCC equals to 1.8 volts. I'm just going to write down over here. So R1 equals to 2K ohm, R2 equals to 1K ohm. And my IS is 10 to the minus 16. So these are the parameters. Give me a moment. So we want to calculate what is the collector current or base current. So if I'm following this first model, it will simply give me that, I'm using the first model, assuming that Vx will simply be 1/3 of 1.8 volt, which is 0.6 volt. And then I can actually calculate the collector current. The collector current will be IS exponential 626. And this will approximately give me about 1 microamp. About 1 microamp. The current level is very low because my VB is very low. And this will then correspond to a IB. I forgot to give you beta 100 default. So this will be 0.01 microamp. Okay? So if you're considering this effect, you can do the correction later. So then if I'm doing the correction, my Vx will simply be 0.6 minus 0.01 times R1 in parallel R2. That's V7, and that's R7. This two in parallel. So this will be very small. So this will be 0.6 volts, and this will be, let me give you a number. This is 7 microvolts. So just to give you that, the correction, the voltage across this resistance is very small in comparison to this overall voltage. So you can simply ignore that volt. And then you get very close to 0.6. So this exercise is simply to tell you that if you're not biasing your circuit with an extremely large current, or you're not using very, very high resistance, for example, mega-ohm resistance, then typically you can actually ignore this effect. Okay, base current effect, because base current is much, much lower. Okay? You good? Questions? Okay, then we're going to talk about the third type of biasing scheme. So this is sort of like a variation of this previous type. I didn't actually talk about why this is not the, or I should say, what are the drawbacks of using this type of design. So you go back to the one that the parameter you actually wanted to control the most. What we actually want is the precision setting of collector current. So what are the unpredictable parameters in this equation? First of all, IS, even though I give you a number, is also not a very well controlled parameter. And the other significant problem is actually Vx is in an exponential equation. So any variation in, for example, VCC, let's say, where does the VCC come about? It's your supply voltage. Remember we talked about ripple voltage. So if you have a supply voltage that come in through ripple and through regulator, you can suppress it down to maybe 10% variation. So that accounts for maybe 0.2 volt variation. So these 0.2 volt variation will actually come into your current and then make your current, your biasing current is supposed to be a DC component varies throughout the supply cycle, for example. So this is not actually a very desirable parameter because it's very sensitive to Vx. So if you have a small variation in Vx, it doesn't matter where it come about. They're actually inside exponential, therefore your IC control will then be amplified. So then larger delta R. So that's the stability consideration, how you actually be sure to improve stability. So when we talk about how you actually can make your circuit more stable, less susceptible to changes in an environment. So this structure is very often used in bipolar circuits. It's called the emitter degeneration circuit. It looks something like this. So it's an identical circuit. We use a divider to actually design or set our biasing point. But instead of having the emitter connect directly to ground, we then add, we call it RE. So this particular structure of adding RE is called degeneration. This structure is, add the emitter, you add a degenerative module. So you actually see the effect. The reason why it's called degeneration is it's very much like a faucet that is water saving faucet. It's a little bit like that. You add a knob to make it less sensitive. So we're going to talk about the structure or the circuit a little bit more later when we talk about amplification. But let's just talk about why this is more desirable. So what it does is that you would then have, in this circuit, you would then have your voltage, I should say, collector current be set by Is exponential. There will be a Vx, and then there will be a Vre. Okay? So your voltage would then be set by Vt, or Vx minus Ic. I should write it this way. Okay? So I want to write it as 1 plus beta IC. This is essential. I just want to make sure that you understand what it is. This is essentially 1. The collector. Okay? So in this equation, you actually have collector current here, and it also depends on collector current itself. Okay? So what does it represent, or what is the implication of this type of circuit? The basic, so you can actually set it up at a particular point. And the generation circuit actually have a particular behavior. This is we call it negative feedback. I don't know if any of you have taken courses like control system. Any? Control system. Okay. Anyway, so just to give you, this is also part of the circuit design. One of the, I should say, key component in circuit design is to how do you actually stabilize your signal. So in order to stabilize the signal, one of the most important things is what we call negative feedback. What's the negative feedback? Meaning that if I'm standing this way, and if I'm pulling out to the left, there's a force pulling me back. That's called negative feedback. If I'm going the wrong direction, and there's a force pushing me forward, then that's called positive feedback. So if there's a force pulling me back, then I will be able to maintain at a straight line, for example. Okay? So negative feedback in here, I'm just going to go through very easily to talk about this. If you think about it, if there's a variation, if there's a change that's undesirable, is hit by lightning or whatever. So let's say if my Vx raises, what happens is that you assume that the base voltage raises, right? So then what happens is that my current is expected to increase. If there's a small variation on the X delta, the voltage increase, current increase. Once the current increase, what happens is that the voltage on the emitter will actually raise as well because the current actually flows to here. So therefore, my VBE, remember what VBE is. VBE is Vx minus Vr. Right? So that's not. So let's say if this is not increase, you expect your current to increase, then this will follow. There will be a slight increase on the resistors, which would then reduce the increase on VBE. Therefore, it would then lead to IC. So that's what I call a negative feedback, meaning that there's two forces. One force pulling the current up, the other force push the current down. So then it will reach a balance and then form a negative feedback to stabilize the output. So this would then give me a more stabilized Vx current level. Okay? So it will actually narrow down the difference. If there's a difference between for circuit 1 and circuit 2, there's a difference. Through the circuit, I will be able to stabilize and make it converge to a more precise or tightened distribution of current level. Okay. So I'm going to go through a last one. We're going to talk about the fourth type of biasing circuit that's being introduced. Example. So then, let me draw the circuit first. Okay, so this will be my particular node. This is called a single stage biasing or self-biasing state, meaning that I don't need an additional branch. In these type of circuits, we actually add an additional branch for the biasing. Here I'm simply having one branch of current that simply splits right here to provide base current to allow the circuit to be functioning in active mode. And then it self-biases itself. Okay? One of the key characteristics of this circuit is that because the current, you expect the current to come down here. This will be IB, IC. This will be IB. And the current here will be IB plus X. Right. So it will supply the whole branch. It will be same as emitter current. Okay? So first of all, you want to see what is the voltage on Vy. Vy is actually set by Vx plus IVRD. Okay? And because we were sure that the current is flowing from positive to negative, therefore this means that your Vy is much higher than Vx, meaning that your DC junction is reversed. So that is a good thing to guarantee that Q1 is in X. So you don't actually, if you're using this type of circuit, you don't actually need to check whether your setting will actually pass this down to into saturation. The circuit will never be in saturation. For example, if I'm giving you the circuit with this type of setting, and ask you whether which region you will not be operating. It will turn off, but it will never be inactive because this junction will never fall rise. Okay? And the other thing is that, and how do you determine your current level? So then your current level will then be determined by Vx set by. So let's write down the equation, the current equation Vy. The other Vy equation will simply be VCC minus IC IB plus C. And through these two equations, we'll be able to solve for IC. So let me simply write down the approximately IC. Ignore the base current. In fact, will simply be VCC minus VBE plus C beta. Okay? So through these two equations, and Vx equals to VBE. If you're using constant voltage model, then you can actually set your collector current through this equation. Okay? So it will be the benefit of this circuit will be it will also susceptible to changes in high voltage, but it will be less susceptible to beta because beta will be in the denominator. Okay, 1 over beta doesn't actually account for a lot. So there's two benefits. One is to make sure that it's always being inactive. The other is that it will be less sensitive to beta compared to the first version that we come up with. So there's various ways of designing your biasing circuit, and there's pros and cons in each one of them. 我有大概2分钟，我稍微简单的 summarize 一下，就是说，在做 biasing circuit design 的时候，那大概有几个重要的考量，我先讲一下。第一个呢，就是biasing 本身就是说我要把它放在我要的点，那所以呢，我希望我能够每一颗电路，不管它长怎么样，因为你做的时候，你做好一个 design， 它定很多啊，大家知道 IC 设计。做好就做一个100万颗元件，所以你希望100万颗的电路出来都要很稳定，所以stability是一个很重要的东西。那大概有几种 biasing 的，我们大概会讨论几种 biasing， 但是我只是跟大家讲说，我们最后你大家都不会用到这个，因为这个是就我们还没讲到真正大家怎么做。那可是呢，但是至少你要知道怎么分析啊。我想这个至少你要知道怎么分析，因为在 IC 里面我们大概不会用这个。所以，但是这里都要用电子图跟字面比较简单。那先讲一下，就是几种 biasing 的考量呢，主要就是第一个就是你怎么样去决定你的电流，是由什么 parameter 去定这个电流。那大家要知道说什么是 determine 的 path， 就像我刚才讲这个东西，就是说，大部分如果我给你 VB， 这个 path 就是定，所以这个定的话，你就知道这个跨压跟这个跨加起来等于 VCC。通常 VC 是一个 undetermined。因为它是有什么决定？它是有 early effect 是 secondary 的 effect， 所以通常这一点都是开放，这一点就是 option 让它摆，所以它的范围是 undetermined， 所以我们一定是用 determined 的 path， 就是 BB 这个 pathway 去决定。所以你要知道怎么分析比较重要。那当然我会讨论一下说，为什么要做各种不同架构，它会有不同的优缺点。譬如说，你不希望说你这个稍微变动一下，它就可能。原先是在 active 变成不在 active， 进入 saturation， 这就是我们通常不想要的。那另外呢，还有就是一些 power 的考量，就是你到底花多大的 power。所以通常大部分情况下，我们会告诉你说，你有多少 power 可以使用在这个 stage 里面，那你就去决定说你的 biasing， 因为左边要用多少，右边要用多少，你的 IC 的最大范围是多少。所以 power 也是一个 limitation。那最后就是 degeneration， 我会稍微讲一下，因为我们后面会用到这个 degeneration circuit。刚才有讲 degeneration 实际上是我们把它用来做放大器。那这个 degeneration 用的比较多是BJT 的电路。那原因是因为它是一个，它像那个我刚刚讲那个省水龙头，就是水龙头有一种，就是你把它绑一个橡皮筋这样，让它比较打不开。所以它那个 RE 就是像绑橡皮筋这样。就是那为什么是 BJT 要装省水龙头？你知道为什么？为什么 MOSFET 我们后面有没有讲？我们之前有讲，就是它是爆冲型，它是 exponential 是爆冲型，就是我打开它已经爆冲，那它一爆冲呢，它就会有很多问题。爆冲就是说它稳定性的问题哈，然后另外呢，爆冲就是很容易会有线性度的问题。所以因为它爆冲的关系，所以它比较需要加省水龙头。那另外一个水龙头，它本身就是没什么水。所以也不需要这样，对，所以这个是大家要记得，要一个 impression， 它是我们叫做 both device， 它第一个它是跟面积有关，第二个它是 exponential， 就是 exponential， 对，它是 exponential dependency， 所以就是 exponential 就是爆冲嘛，所以你要让它不要那么爆冲，就是要加一些东西。所以我们会常常看到，如果你回去看经典741，我们第一课讲它就有加，经典741 ，OP 741。TC 里面就会有加，所以很多那个 bipolar 的 circuit 加的比较多，那 MOSFET 偶尔会加，但不是很需要。那我们等一下会看到它的小讯号放大的模型，那只是加，就通常加这种就是抢回来的力量，因为你加橡皮筋就是这边是我的开方向，我加的橡皮筋让它 增加阻力嘛，所以你越转它越往后面拉，所以它是一个我刚刚讲负回授的概念。负回授就是让你不要那么敏感，就是有一个回拉的力道，好不好？那我们先休息一下，然后来讲 survey 这件事，就是看 raw signal 的行为。零点四是 VCE 1.8 volts. Maximum gain under 1 milliwatt. Okay? So what we need to pick in this biasing circuit is RB, RC. Okay? So for transistor, depending on the model we're going to use, for this we're going to give you VBE. So use constant voltage model. Anytime this bound is given, meaning that you use constant voltage model to define. So this will be 0.8 volts. And then VCE, this will determine whether your device is operating in saturation. And then of course beta. Okay? So what is the power that we need to dissipate? The power will actually limit the maximum current. So this is IB, IC. So the power will then first determine what is the target biasing current. So power dissipation will then be VCC, IC, IB. What equals to 1 milliwatt. Okay? So we can actually get our current. IC will be approximately 0.55 milliamp, where IB will be let's just say 5.5. Did I get it wrong? Sorry. This will be so then, yeah, I did it. So 100 time difference. So once I have this number, I should be able to get the resistor level. So then I can pick my resistor. So first of all, how do you pick R? RB will simply be VCC divided by minus the voltage drop divided by IB. Okay? So I didn't get the number, you can get it yourself. So you can determine the current level. It will be 1.8 volt minus 0.8 divided by 5.5. Okay? So you can pick the resistor level, RB, but how to choose? How about RC? RC will be the maximum level where you will stand. To get the maximum level, meaning that you need to find out IC max. So what determines IC max is actually the gain. We want to have, remember what is the target of this design is to obtain maximum gain, meaning that you want maximum IC. My current is, okay, let me say this. The voltage gain of this circuit, I said the absolute value will be GM RC. So I already know my collector current, so which is IC versus V. So to get maximum gain simply means that you want to reach gain maximum. If it's an absolute value, then this would then, to see what is the maximum level of your collector resistance. So IC maximum will then give me the maximum gain. Okay? So how does one find it? What limits your maximum gain? It's limited by whether your device will be operating in saturation. So the maximum gain, the maximum resistance will be VCC minus VCE set That's at the boundary. Remember, I'm standing at the edge already, divided by IC. Okay? And this would then give me 2.5. Okay? So my final design will be something like this. This is my final circuit. This will be 2.52 kilo. I don't know what this number is, but this will be an RB level. And then this will allow you to stand at the edge to give the maximum gain. Okay? So once you insert that number, you can get your maximum gain. The GM is about 21 milliamp per volt, which will give you a voltage gain, AV max, would then be about 54. Okay? So what does standing at the edge imply? I want to do a small exercise. So let's say as part B, so after design, this is your design problem. Then I ask you to draw the output. Okay? So let's say if I give you an input at, let's say my V looks something like this. It will bias at VB1, which is 800 millivolts. This is my DC level, plus a, so V in will be VB1 plus a small signal. Let's say if I'm inserting a small signal into the system, 2 millivolts. Okay? What do you expect your output will look like? So this is versus time. So if I ask you to draw your output, this is VR. This is time, VR. As a function of time, we know that it will be biased at 0.4 because VCE is 0.4 and it already surpassed to the edge of the stage. Okay? So ideally, what you expect is this is the DC level is 0.4 volt, and then it's supposed to amplify by 45 times. Therefore, you're expecting the amplitude to be, let me draw the line. Let's say this is, so the amplitude is about 100 also, 2 times 54. So it's 1.8. So you get something like this. Inverting, I'm not lying, but it's an inverting amplifier, so it will be something like this. Okay? This is what I expect. This will be somewhere close to 0.5. This was somewhere, okay? So this is based on small signal model. GM RC. Okay? Do you think that this is the correct answer? Yes or no? What do you expect it will look like? It's supposed to be a sine wave and amplified by the gain of 54, right? Do you think that this will be something that you'll see, or what will happen? 你觉得这是对的吗？正负为什么会属于线性？正负就是线性，我们就用线性模型。线性模型我们算它电是14啊，所以它应该放大差不多50倍，所以应该正负要0.1伏，差不多啊。你觉得 这样对吗？我这样问很害怕。Like I said, the problem with this question is it's sort of a trick question, is that because I asked you to design this to provide maximum gain, but I didn't give other specification. The problem of having maximum gain is that you have to stand at the edge. So if this voltage, the output voltage is lower than 0.4, meaning that Q1 is inside, by definition. So what happened is that you actually see a response look something more like this. When you're not in saturation, it will be fine. So this will be fine, following our model. It will not be larger, but it will basically be whatever we predicted, mostly based on small signal model. But what happened here, it will be like this. Okay? So this will be more like the real case. And the main reason because of this is because it's falling down out of the stage. You're not supposed to use this Maxwell model. It doesn't work anymore. So the only valid vision is here, positive. So this is typically referred to as what you sing when I talk. When my voice saturates, this is called a distortion. So that's the risk of standing on the edge. It's like my voice, it's distortion. But this is the same thing, you're hitting the wall, you're hitting the edge. Okay? So to prevent this from happening, what you actually want to do to find the operating point is not typically limited by one specification, because if you're only looking at, for example, power and maximum gain, you actually didn't see other possible problems. So the more ideal way of finding a desirable operating point is to do a survey of the whole stage. So how does one do that? It's actually not that straightforward. I'm just going to use the same example. So let's say if I have a circuit look something like this. So we want to do large signal analysis to get the whole rail-to-rail behavior of the whole stage. Okay? So let me this is actually a simpler way of doing this. Then tie an RV at the input will actually make it easier to work. So what is actually being done, if you actually have the circuit, what can be done is that you simply sweep your input and then look at the output, the DC level. I want to see the whole transfer characteristic. But what if you don't have the circuit, you simply have the models being given to you? So this type of the model here, we're going to use VBE on. Let's say it's 0.8 volts. And then beta equals to 100. So how do you generate your transfer characteristic? Simply based on this sweeping. So I want you to draw VL as a function of VE. So how do you approach this problem? It's fairly simple. You simply write down the equation, or it's a graphical debating whether to go through that. It's a little bit complicated, but let's go through the equation part first. So how do you actually determine VL? So you write the VL equation. VL will equal to VCC. Simply from here, we know that this is IC. So VL equals to VCC minus ICRC. So if it's inactive, there's various components, I should say operating region. This is when, so let's say, when V in, there's different, I should say, sort of like a piecewise linear method. You separate into different regions. So if V in is smaller than VB you assume what happened. If V is smaller than VB this device is not turned on, which we assume that Q1 is in cutoff. Based on the constant voltage model, when it's smaller than VB it's cutoff, meaning that IC equals to 0, therefore V out. You should be able to draw a curve. So I'm sweeping this V in from 0 to VCC, for example. I don't know what the number is. 3 volt. Let's say this is 3 volt. And I'm going to give you parameters. So let's say RC is 10K. I'm using a large one. Okay. So as I said, when you're in region 1, which is this is smaller than VBE which is 0.8 volt. So when your input is lower than 0.8 volts, we assume that current equals 0, therefore output equals to what? VCC, correct? So you start with VCC, which is 3 volt. So this is V out. Okay? And then when it's higher, so this is at a high level, this is barely turned on. When it starts to move to higher than VB out. So we assume region number 2, so this is region number 1. Let's see what happened in number 2. So once you move on to V in larger than VB on, you assume, we can do a guess, assume that Q1 should be inactive because my VC is high. This one is high. This is at a high level. So you basically have sufficiently high enough reverse bias across this BC junction. Inactive, therefore we can use this model. We can use beta essentially. So then your current VL will be VCC minus RC times beta IB. So what determines IB? As I said, it will determine by Vn, therefore VCC divided by, let me write it down this way. Beta RC. What determines IB? IB will be determined by Vn minus VBen divided by okay? So you do some rearrangement, you can actually get the equation look something like this. This will be VCC RB beta RC Vn plus RB okay? So you simply, these are constants. This is constant, this is constant. You simply insert a number and this will be, the slope will be determined by this, right? So you can simply write down your equation. So once I insert all the numbers, I actually get VL. Let me write down the equation. If I'm based on the parameters given, the VL equation will simply be 11 minus 10 VL. I'm just inserting whatever number that's given beta, alpha, resistor levels. So what does that imply? This equation, I should just write it down over there. So in region 2, the equation is VL equals to 11 right? Minus 10. So what is minus 10? Minus 10 simply is the slope of how it drops. So it should drop at a rate of minus 10. So the slope is minus 10 volt per volt. So how far can it go? It goes when it hits, based on our model, VC, the criteria of making sure that the device is operating in saturation is 0.4 volt. We're going to use that consistently, I should say, throughout this class. So then it will then drop until it hits 0.4 volt. So then it will then enters region number 3, which is Q inside. This is off, this is active, and then inside. So 3 operating regions. After it reaches saturation, if you actually measure it, it will actually drop slightly, gradually down, but you can use a flat line if you want, that's fine. 0.4 or 0.2 doesn't really matter, because it doesn't have any amplification impact. So what are the important parameters in this overall transfer characteristic? There's basically 2 important information. One is, how much can I move in order not to move out of the stage? So this is called the input voltage range. So you need to be able to find out what is the input voltage, the available voltage range. So we know that it starts at 0.8. And how do you determine the other point? I know the slope. Therefore, how much does it have to drop? It has to drop 2.6 divided by 10. So this will be 1.0. Okay? So this is based on the slope to determine this point. So this is the room where you could place your input level. Input biasing level or swing level. So this is called the input range. Input voltage range. For Q in active. So you want to make sure that this is the actual amplification range. And the other thing, of course, is your swing. What is your swing? Is how far can your output, how far can the performance go, which is my output. So we typically project this. This is typically referred to as the output swing. So it would depend on whether you're dancing or not. If you assume that your output swing, if you assume that there will be a large output swing, you want to make sure that you need to stand right at the middle. This will be your best operating point to get the maximum swing. Otherwise, you will hit the wall, whether on the left side or the right side. Okay? if I'm revising the question, says that find set. So part B will be set the operating point for maximize swing, output swing. Meaning that you have to stand right at the middle. That means that my output DC level, VC, the collector voltage has to be set right in the middle. So that will be 1/2 Vmax, VO max, VO minimum. So what is my maximum output voltage? Maximum is VCC, correct. Minimum is VCE set divided by 2. So this will set my biasing point at 1.7 volt. So then I have a swing of 1.3 volt. That is VCC minus VCQ. Okay? That's called a swing. How much can I swing my output? And then eventually, what's supposed to be my ICQ will then be determined by VCC minus VCQ divided by RC. And this will be 130 micron. So this will be where you want to place your biasing curve under this particular setting. Okay? So this is how you actually survey the whole stage and then determine what is important to you. As I said, if your signal is very, very small, you're not expecting to swing too much, you can still work at the edge. So if, let's say if my signal is microvolt, so then I could simply biasing a little bit higher, then my output signal can be amplified still, can get the maximum gain without distortion. But if I'm assuming that I'm going to swing, my output is going to be amplified to a large level, my input voltage will not be very, very small, then you have to consider whether to set it to a more appropriate position, allowing the signal to be completely amplified without significant distortion, as I said, when you're standing at the edge. Okay? Is good? So you should have the capability of determining. So what is the key point to capture in this type of analysis to, based on the specification of the question, design question meaning that what I'm aiming at. If I'm aiming at maximum gain, this will still be a valid answer. If I'm aiming at a maximum swing, then this will be the place to place your operating point. 我简单稍微讲一下，就是说。在决定 operating point， 刚才我们讲，你用 biasing circuit， 你可以去设到你想要设的地方，看你用电阻啊，或是用比如说电压、分压的方式去设。可是你要设在哪里，就 depends on 你的 spec。spec 通常有2种，一种就是 power，power 的 spec 就决定你的电流，另外就是 gain 或者是 swing。那所以呢 gain 的话，就我们刚刚讲，如果你是 maximum gain， 你可能就要站到边边。那但是你可能一开始如果讲话很小声，你可能不会破音啊，跟你讲话大声就破音。所以这个是这样的 design 的问题，所以你要了解说，所以你可以这样做，这也不见得是错的。所以你就说，如果我的讯号本身就是非常微弱，讲话就很小声，那怎么样也不会破啊，你不太会破，或者有一点点 noise 我可以，有一点 distortion 我可以接受。但是如果你希望你的 performance 是假设你的 input 讯号本身相对可能比较大，比如说可能在0.1，像这个的话就是你的操作 input range 比较大，比如说。200个 millivolt 左右，如果你的讯号本身相对我讲话比较大声，那我就要担心我会破音嘛，所以我就要站在中间，然后确定我的声音可以扩大到那种4.5。所以这都是 depends on 设定，也就是说我要求什么，所以大家要看清楚题目。如果你纯粹用解题的角度来说， 就是说你要看清楚题目要求什么，那它的 limitation 在哪里？它要求你要怎么去看这个问题 ？OK， 所以决定 operating point 就是通常是我简单讲啊，就是如果出的题目，它就分3个小节。第一个小节就是说我给你固定 power 去决定电流，决定电流之后就是小讯号分析，然后找它的 input output，它就是3题，懂我意思吗？所以我们现在已经解第一题，就是说你去决定你的 operating point， 然后呢，你把你的 setting 设好。不管你怎么做，比如说你去设这个 input 的电压也好，你去设，假设我们刚刚用 biasing circuit 这种电阻去设，把它设在那个位置上，这是第2题。第3题就是小讯号分析，所以我们等一下要开始做第3题，这样懂吗？好。Start the discussion on small signal analysis. Once you already know how, what are the parameters that determine where you're going to stand, the next question is then, based on this circuit, we're going to use this as an example. So how do you actually do the small signal analysis? So the small signal model of the circuit will look something like this. So simply, you should be able to do the third part. I've already set my operating point, and the third part will be sketch the small signal equivalent circuit. Okay, so if I'm simply going to extract this as my small signal, common emitter small signal equivalent circuit, it will look something like this. We probably already go through that in our previous example. This is R pi, GM, V pi. This is RO. And this is ground, and you're connected to another RC. If I'm including that into my stage, this will be whatever is being inside this box, right? So then, you should be able to turn this whole thing into a equivalent model, a two-pole model with Rin, as I said. If we're assuming it's a voltage amplifier, R out, AVO. So what you need to do is that, based on this model or this particular circuit, you have to be able to find the 3 important parameters, which is input resistance, open circuit voltage gain, and output resistance. So these are the key features of amplifiers. Okay? So based on this model, what is the input resistance? I'm simply looking at, I don't need to find the number, I'm simply looking at this parameter, what is Rn? Based on this small signal circuit. Can you actually see it? What is Rn? Rn is that you give it test voltage and look at its test current, right? So big. Why is it confusing? I'm simply transforming this into the small signal model, right? So this is a small signal equivalent circuit. Well, this is Q1. This is Q1. I'm only adding a resistor to ground, right? So what is Rn? You're simply looking at this, what is Rn? Anyone would guess? This is very simple. 猜一下 ，What is RM? Correct or not? So you don't actually need to do anything. This is very simple. That's why I asked you. So this equals to R pi. If you actually do this exercise, you will find out it's simply this, because whatever you apply will simply modulate the current across here. So what is this gain? You set this to ground, and the gain is simply input and output when the output is open. So the gain, you can actually do the exercise on your own, but the gain will simply be Gm times whatever you see at the output terminal, which is RO in parallel RC. Okay? And output resistance was simply, I'm turning this off and looking at the output terminal. So when you turn this off, this is closed, and this will simply be RO in parallel RC. So this is whatever happened to a simple common emitter stage with a load of RC. So this is the third part of the question. As I said, typical question for a single stage amplifier is that you start with picking up where you're going to stand, and you set the point. How do you set it? Once you set it, the next question is to find out its input resistance, output resistance, and voltage gain. So you simplify the overall circuit with this model to understand the input, output, interfacing, and its intrinsic gain. More like an intrinsic, because open circuit is the maximum gain you can get out of a single stage amplifier. Copy it again right here. So RV will be right here. Okay? So you asked a very good question. So what if I want to find out if a signal is connected to here? So if I want to find out, instead of open circuit voltage gain, I want to find out VL. For example, if this is connected to a load, and this is connected to RV. So if I want to find out this, okay, so that would be the fourth part of the question. So once I have all this model, I can simply use that. So VL versus VS will simply be RV plus RN AVO times R out plus R load. Okay? So that's how you get the complete answer when you actually connect it to a source with RV and output with a certain load. So this will then give you a general behavior of a single stage amplifier, and then you can connect to whatever you want. So whatever next stage, the input stage, R low may be the input impedance of the next stage, or simply a loading that you're connecting to. So then you simply use this to get your overall response. So this too is mostly interfacing quality. So how do you actually design this? As I said, you want this to be as high as possible, as low as possible, to get close to this. You get that? 所以真正我们通常我刚刚再讲一次，就是说一个经典的考题，在这个 chapter， 我再讲一下，就是我会给你一个电路长这样，然后呢，我们大部分不会要求大家画这个，因为画的太麻烦，所以，但是呢，你要大概知道你的 boundary 在哪里，你要先知道说，你最高最低在哪里，这个范围，如果有的时候会问这个，你去看这种放大器的经典考题 single stage。所以第一个就是这个，然后那你就决定，我会给你的条件，譬如说我要 maximum swing， 我要最大的 gain， 然后你就去决定你的 ICQ 决定好之后，你就可以决定小讯号模型。小讯号模型出来之后，你就可以知道这个 stage 本身先没有接到外面哦，所以不管 bias， 你就是看这个 stage 本身，它的 input impedance、output impedance， 它的 gain， 它就可以变成那个模型，然后再把那个接上去，对，看你前后要接什么。 那到时候你有譬如说2、3个 stage， 那这边就是接下一级啊，下一级要 input resistance 就是你的 output， 就是可以界面可以接下去，就可以堆积膜了。所以你一定要知道，就是说我再讲一次，就是你要想象你这个都是一个我们叫做 building block， 像你的积木一样。所以你要有积木基本的特性，是不是就是颜色，就是它的电。可是你积木前面是1根头的还是3根头的，就是要跟别人接啊。所以这个就是跟人家接的时候的特性的 distribution， 跟前面接跟后面接特性的 distribution， 你要确定你后面接的跟前面接的要 fit， 如果不 fit， 你就可能会lose 很多东西。所以这件事情就变得 interface 变得很重要。所以我们一定不能只看片，我们要看前面的头是怎么接，后面头怎么接，接上去不会出问题。这样懂吗？你本来要讲，人家没有时间讲。所以我跟大家讲，就是说，基本上你要做的事情就是 follow 一个 analysis 的 procedure， 应该这样讲。procedure 就是我再讲一次，一开始先看条件是什么，我给什么条件决定你要站在哪里。你知道站到哪里之后呢，你就可以去得到小讯号模型，把小讯号塞到这 Q1 里面。然后通常我们会看你要切哪里，就是说很多种切法啊，所以大部分我比较喜欢就是我就是把这整个 stage 有包含 bias 这个 RC 这个算一个，那你也可以把它包进去啊，如果把它包进去你就把 RB 包进去，但是不管你包大包小，结果都要一样 consistent。因为它是一个等效的意义嘛，所以你可以把 RB 包里面，你可以把 RB 拉出去，或者说像这个 case， 我可以把 RC 拉出去，就是 RC 我不要算在里面，我就先做这个，然后再把 RC 放外面，结果要一样，它是等效，所以你可以把 RC 算到外面去啊，你也可以把 RC 包在里面啊，但是包在里面包外面看你习惯。所以通常正常的做法是会把 RC 放在里面，就是假设我讨论说 single stage 本身 intrinsic 的 gain， 因为它是我的 bias 的一部分，所以通常会把它放里面。可是你不要放里面也可以，好，那但是我应该这样讲，就是说，如果你放里面放外面算出来不一样，就是不用收拾，因为它应该一样，它就是一个等效的概念。你包里面包外面，最后结果都会是要是一致。OK。好，我想看大家都好像很疑惑，所以我就不要继续讲，今天就讲到这里。然后呢，那我们因为我要讲的东西更难讲，我有点不想要让大家已经快要不行了。